BioSentinel, I'm currently still the PI of BioSentinel, I believe. Launch, as all of you know, SLS Artemis 1 on November 16 last year. So it's been pretty much 6 months since we launched. Um, one more, please. So we had two actual launches, two missions associated with BioSentinel. One on ISS that we launched on December 2021, and stay on ISS until August. This was a control testing of all the hardware, the electronics, the data, the scripts, etc. So this ended in June last year, but we had the payload back in August. We had some minor issues with this payload, particularly on our last experiment, one of 9, as you will see in the next slides. And of course, Artemis on November last year, currently at approximately 17 million kilometers away from the center of the Earth, still nominal, still functioning. One more, please. BioSentinel, I mean, all this has been published, so feel free to look at our open access publications. Inside, there are a lot of components, primarily everything that needs to survive in deep space, to survive to the cold environment, to be able to contact the DSN, send the data back, and of course, the main focus being the biosensor unit that contains a series of microfluidic components to support life experiments. And of course, another objective is to study the radiation environment, for which we have a spectrometer that measures both the amount of radiation, the total dose, as well as the type, so the spectrum of radiation particles in space. One more, Ryan, please. One click. This is a different components. This has been published before, and we had the unit on the ISS at the bottom left. There are 18 fluidic cards that have biology inside. In this case, the budding or brewers yeast Saccharomyces cerevisiae, that they were pretty fine on the ISS. However, on the free flyer, we noticed early on around Christmas, so a little bit over a month after launch, that we're starting to get some electronic measurements that were kind of off. And then one more, please. Then when they're discovering that it has to do primarily to an increase in potentially an increase of the humidity inside. What ended up happening is we continue pushing to try to fill fluidic cars. We successfully fill a few of them, I believe 4 to 6. We did not observe cell growth, unfortunately. And we were kind of, it was a big bummer, but we kind of had an expectation this could happen just based on what we observed on the ISS in terms of humidity increase and the duration of the time the biology was sitting inside this box, inside the rocket at ambient exposure, so humidity, temperature, etc. This slide shows you the LED spectrometer data. What have we obtained so far? So we did some modeling publication recently that estimated to be 0.25 milligrade per day of radiation total. We have observed more. As of right now, we are probably reaching the 60 milligrades or 6 centigrades. That is more than we planned, and this is because having multiple solar events, and we have captured all of that. We'll be publishing this in the upcoming months, and we'll make all this data available to the community in terms of all the radiation, not just total absorbed dose, but also the spectrometer, the spectra data from the machine. One more, please. And of course, this just to show the characterization of the first 49 days, the spectra going all, from low energy particles all the way to high energy particles. And so nothing special, but pretty exciting being able to capture this data on such a small spacecraft. And even though it's not official, we are potentially getting an extension for at least another 6 months to record more data, reaching towards a solar maximum, as you all know. One more, please. Just an example of we observed in terms of solar particle events. On the bottom right, it's our spectrometer just measuring, in this case, absorbed dose rate. And you can see the increases when we got, in this case, 2 coronal mass ejection solar events in February. One more, please. Very similarly, we observe another longer duration solar event in mid-March, and we're able to record that data. We still need to analyze all this. One more, please. One more, please. I told you about the issues and lessons learned. And what does that matter? You can do one more, please. What does it matter of what we have learned from BioSentinel, the successful in terms of technology demonstrations, validation of the technologies, the electronics, the optics, and all that stuff? communications, data management, processing. It has helped towards this mission, which is LEA. The Lunar Explorer Instrument for Space Biology Applications, we were awarded, my co-PI, Mark Settles, and myself at NASA Ames, were awarded this mission to lunar surface on Eclipse lander in 2026, and it's based on BioSentinel, and it's going to have an additional LET spectrometer as well as a mini fast neutron detector to characterize that radiation environment on the surface of the moon. And of course, biology, try to characterize the response and the production of bionutrients or synthetic biology characterization. And we're trying to improve everything we learned from BioSentinel for this mission in terms of improve desiccation tolerance of the biology, improve desiccation tolerance or humidity tolerance of the electronics, and so on. And I believe that's my last slide. So we have generated, again, an instrument that we went to ISS, so lower orbit, trying to go to lunar surface, and of course into deep space. And we're hoping that it gets in other places. And I have one more slide, I think, if you guys want to watch a video, but you can probably click, I think, one click. That's the launch on November 16. I'm sure most of you, if not all of you, have seen it. I like the bottom video better because that's mine. That's all I have.